Okay, good morning, everyone. Welcome to this IFAD 2020 lecture, which will deal with how crystalloids fill the intravascular space. My name is R Hahn. I live in Sweden, and I've been very interested in fluid balance for many decades. I will tell you now a little about what I've found about this topic. First of all, crystalloids don't fill up the intravascular volume, it fills up the plasma volume, which is just a fraction of the blood volume. We have this relationship, I'm sure you've seen it before, but it's not a whole truth. Now, the crystalloids fill up a lot more. That was found many years ago, of course, and was quantified by this group of F.T. Moore in Boston. They used tracers to study the relationship between the plasma and interstitial fluid distribution of crystalloids, and they found that the 4.5 times larger expansion of the interstitial fluid than of the plasma was the case. We have, which really does mean that the plasma volume expansion is not very impressive. Most of the fluid ends up outside the plasma. We have later studies showing you just about the same thing. The plasma volume expansion is below 20%. That's not much. It's not very effective at all, actually. Well, I claim on my side that crystalloid fluid is a very short-acting plasma volume expander. And we'll now take a look at using a kinetic model that I invented in the early 1990s and have worked with since then. We will now use that one to take a look at what happens and how I can claim that it's still an effective plasma volume expander. The kinetic model looks like this: that we infuse fluid into the plasma, which is a volume central here, VC. And we have an interstitial fluid space here, and the exchange occurs by a capillary leakage rate here. We have a redistribution, which might be mostly lymph, at least in resting human beings. We have urine excretion by K10, as you see here. Now, one early finding with volume kinetics was that this volume was much smaller than originally reported by Moore. Because most of the interstitial fluid space cannot be expanded by fluid volume. We can think that the bone tissue, for instance, cannot be expanded. We have the skull cannot be expanded. We have several organs in the body that are enclosed in tight caps that cannot be expanded. So in volume kinetics, we count on that the VT is about twice or a little more than twice as large as VC. Capillary leakage of crystalloid by the mechanism K12. We're going to take a look at that. K12 times plasma volume expansion is the capillary leakage induced by the increase in volume. And a typical value of K12 is 0.08. It varies between 0.04 and 0.1, so there's a variability here, but 0.08 is a typical value. It means that 8% of the volume expansion is filtered every minute. And as you know, the circulation time is about 1 minute. It means that for every passage through the capillary system, 8% is lost. So the first minute is 0.08 times 500 milliliters. If we assume that we have a plasma volume expansion of 500 milliliters, 40 milliliters will be escape the plasma volume on the first passage through the capillary system. We can calculate this by using the factor K, the rate constant K12. So the half-life of this volume expansion is the logarithm of 2, the natural logarithm of 2, which is 0.693 divided by K12. That means almost 9 minutes. And as you know, a distribution function is more than 95% complete when we have 4 half-lives. So 35 minutes, then this distribution function is completed. It's actually completed a little early because we have fluid coming back from the interstitium. So, but about half an hour, that's a good value to remember. Okay, so this is the flow in this direction. Now we're talking about the urine excretion, because that is a very important, the elimination really of the crystalloid fluid. We don't have any metabolism. A typical value here is 0.02. So 2% of the volume overload is excreted every minute. And this is not, of course, the glomerular filtration rate, because that's much higher. This is the finally excreted urine volume. So the first run through the kidneys, we will excrete 10 milliliters of an overload of 500 milliliters. And the half-life is then 35 minutes. Now, this is the half-life of the intravascular fluid volume. In real life, the half-life is much longer because we have fluid coming back from the interstitium, the peripheral space, the VT, as I saw in my previous slide. But we can easily computer simulate the real half-life of this fluid volume. How it looks if we make an integrated plot of this now. Of course, if we infuse crystalloid fluid in the beginning, 100% is left in the circulation, remains in the circulation, but it decreases fast. If we give a continuous infusion over 30 minutes, this is what we find. It's the end of the infusion, then around 50% remains in the circulation. And then during the subsequent 30 minutes, we have an equilibration with the fluid volume in the interstitium. So the curve looks like this. If we had immediate distribution, we'll find the plasma volume expansion looking like this. So this is the benefit, excuse me, that we have by the distribution function, and which makes crystalloid fluid as a pretty effective acute plasma volume expander. But as you see, after equilibration has occurred, which is really what was covered in the first papers that I showed, then the effectiveness will be much lower. So the slope here is made by K10, and the difference between the slope here and this line is K12 minus K21. If we integrate the curves, they look like this. This is the plasma volume expansion. If we assume that we infuse 2 liters of fluid, you see about half of it remains in the circulation at the end of this 30-minute infusion. Then it levels off pretty fast. Next question is, does the crystalloid fluid fill up the glycocalyx layer? As you see, this is a cross-section of a blood vessel. And we have the circulating blood here, we have the glycocalyx, and we have the interstitium outside here. My answer to this is that it fills up the glycocalyx layer, and this occurs almost immediately. And how I can say that, I explored the topic in a paper here that's published quite recently. What we've done is that we have made volume kinetic analysis of many infusion experiments performed in the volunteer setting, very stable conditions, and we can see that the volume indicated is about 400 to 500 milliliter larger than if we use a tracer. Yeah, that's an interesting result. That we have hydration here too. So probably the time it takes for the infused fluid to pass out at the interstitium is located here in the wall, or it does have something with regional perfusion to do. How about if we don't have any glycocalyx at all? Does it make any difference to the distribution? Well, this is a very recently published study in mice. They are deficient in synacan-1 and the data that I'll show you here. And if we make an infusion of crystalloid fluid in them, we can say that the urine volume is going to be much larger in the synacan-1 deficient mice. These are sort of knockouts. Yeah, it's almost double. While the fluid that ends up in the interstitium doesn't differ very much at all. We have both the ratio here, and we have the tailwater concentration here, which is a direct measurement. This is an indirect calculation. We see they don't differ very much at all. So we can say that the syndicate 1 is important to the urine excretion. Well, it's more dubious whether it affects the crystalloid fluid distribution between the central and peripheral spaces. Glycocalyx layer may have much more importance when regard to distribution of macromolecules, but that's a different story. Yeah, the increased excretion in if we have a change of the glycocalyx layer can be also seen here in these experiments. These are females with mild to moderately severe toxicosis of pregnancy. K10, you just know, is the urine excretion, much larger here than in gestational match controls. We can see that the fluid distribution is a little slower in the diseased women. That's probably due to that plasma volume is lower. The biggest difference, though, is the redistribution of fluid that has entered the interstitium simply doesn't return to the plasma. You see there's an enormous difference here in the values of K21. And that's probably due to that inflammation causes a decreased interstitial pressure. We have seen this before in septic patients, and I believe we have the same. We would have the same effect also in burns patients if we measured during the first day after the burns injury. There are also other settings where the turnover rates that I talked about in the beginning of my speech don't apply, and these are more familiar to us. This is sudden hypotension, which we see, of course, every time we induce general anesthesia. What happens is that K12 becomes very, very low, so filtration stops until the increase of the unstressed volume has been filled up, which would be about 1 liter, I would guess. I think this is nicely explained here in the new article this year that you can turn to if you're interested in this to go into detail. Hypertension as such reduces K10 very, very much during general anesthesia, and that lasts until the arterial pressure is restored, which is the case, of course, when you wake the patient up after the anesthesia. This has been explored in quite much detail. The last function I will talk about, this might be a little more confusing because I said a KB increases when K10 decreases. I've seen this effect for many, many years, but I've not made a point of it until quite recently here. So there's an article in press that you can turn to. What it is that we talked about K12, the filtration, we talked about a little about the redistribution, we talked about the urine excretion. We also had another factor called KB, which in volunteer experiments does have a certain value, not very high, but the fluid is kind of leaving the kinetic system, ending up somewhere in the body. We don't know where it is. If it's might be in the gastrointestinal tract, or I don't really know. If we take a large number of volunteer experiments, you'll see here that the dark plots are unconscious volunteers. When the K10, which is on the x-axis here, is high, then we have a very low KB, and when the K10 is reduced, becomes very low, then this factor becomes very, very high. And we can illustrate this in various ways, but there's a reciprocal correlation between the two. So when the urine excretion for some reason becomes very low, we have elimination of fluid that to a space that doesn't equilibrate readily with the plasma or with the interstitial fluid space. Now, this doesn't make that much difference if we have a conscious volunteer. As you see, there's a marginal difference, but the difference increases here during general anesthesia when K10 is very low. And for worse, a lot of more fluid is being hidden because we have the same effect in the interstitium. So I claim that this might as well be, it could be the explanation to why we have fairly long-standing increase in body weight after major surgery. It doesn't have to be hormonal. It can actually be this effect, which I call, without having a better name, as third space fluid loss. I will end up with showing this slide explaining what a normal substitution scheme means to the plasma volume expansion during surgery. If we have a very commonly used scheme with 3 milliliters per kilo per hour, we increase the plasma volume by 200 milliliters per hour. Not very much, actually. So to fill up the increased unstressed volume, we need to have some capillary refill. If we increase it 5 milliliters per kilo hour, we will have expanded the baseline plasma volume by 300 milliliters, and we can keep that quite constant. I think this might be interesting to know that if we want to place this, if we want to have an expansion of about 300 milliliters, we must start with a bolus, actually. Otherwise, we cannot get into that. But that must be given after we have used general anesthesia, because then if we give it before, the kinetics will be quite different and the effectiveness will be less apparent. So with those words, I would like to thank you for listening to my talk. I hope you will have some new thoughts about how the crystalloid fluid behaves in the body and how this is changed during general anesthesia. So thank you for your attention.